The three most important specialized devices that an electronics hobbyist should pick up are a bench power supply, which allows you to specify how many amps and volts you want without any additional fiddling, a multimeter, which allows you to measure volts, amps, and resistance easily throughout your circuit at any moment, and an oscilloscope, which allows you to view signals, such as changes in alternating current, such as checking for interference in your devices, such as viewing logic signals like pulse width modulation that control the speed of a CPU fan. But I don't have an oscilloscope for one very important reason. They are quite expensive. And to be honest, the very beginner absolutely does not need one. Later on, an oscilloscope is going to be invaluable, and I plan to acquire one at some point, or perhaps try and build one, at least a little one, with an Arduino. It certainly won't be as good as a commercial oscilloscope, but it'll be a fun little project. In the meantime, let me show you how to use a bench power supply and a multimeter. A bench power supply is a very simple device, especially if you get a cheapy Chinese one like I did. It gets the job done, perhaps not elegantly, but it's an excellent starting machine and will certainly have paid for itself by the time I move on to something better down the line. This one here has the standard 3 pins. You've got your black pin, which is your negative, or we generally call it 0 volts in DC. You've got your positive, your hot line, as it were, which in this case will be putting out 5 volts later on. The green one, which I'm not using, is your ground pin. This one is just for safety, or for a near perfect reference voltage. Basically, everything electronic that touches ground goes to ground. This one just passes straight through to the ground pin in my wall socket. But like I said, for DC, we don't really need it. So the way this device works, right now I've specified 5 volts. The top is the volt output and the bottom is the amp output. I have it set on 0 amps. Now, first of all, there's no circuit being made here. It's in my breadboard, right here, but I haven't connected between. So the circuit is open and nothing's flowing. If I were to connect a wire through, between the positive and negative, just a pure short circuit, still nothing is happening. And the reason for that is, this is an ampere limit. Right now, I've set it on 5 volts, but I've also set it on 0 amps. So the way the power supply works, if you're familiar with Ohm's law, the resistance is set. The resistance is whatever stuff I have in my circuit. I control that. So what happens is, the voltage starts at 0, and it begins to turn the voltage up and up and up and up. And it's measuring the current. So the resistance is staying the same, the voltage is increasing, which increases the current. If it reaches the volts that I want, if it were at 5, it would stop. We'll see that later. But it reaches the current limit first. So it turns the volts up until it reaches the current limit, and then it stops turning the voltage up. For example, if I were to leave this short-circuited and turn it to 1 milliamp, it will go ahead and do that. It's a short circuit with very little resistance. It's not even reaching 1/100th of a volt according to this. In fact, let's measure the voltage to see what we get. It's reading barely 0.1 millivolts. There is current flowing, but it's the teeniest, tiniest bit because there's practically no resistance. Now let me not break my breadboard. Let's use an LED instead. Connect the positive of the power to the positive of the LED, the negative of the LED to the negative power. I turned my amps back down to 0, so they're at 0, but let's turn it up to 1. And you watch, the LED lights, stops at 2.65 volts. So it has reached its 1 milliamp target by going up to 2.56 volts, which is enough to overcome the forward voltage drop of the LED and light it up with that much current flowing through. If I turn it to 2 millivolts, 3, 4, 5, keep going up and up and up, then it increases the voltage until it reaches that current and it stops again. My limit is at 5. If I kept turning this amperage up to 5, it would go up that high, but I'd be breaking my LED because there's no resistance in the circuit. Turn the amps back down, it turns down the voltage until it's below or at the amperage limit. If I connect this through a resistor, from positive power to one end of the resistor, the other end to the positive of the LED, the negative of the LED to the power, and I'll turn it up. The LED lights a little more dimly than before. It's all the way at 5 volts and it's not even at 1 milliamp. So it has reached the voltage limit before it has reached the current limit. It seems like there's a lot going on here, but it's really not. Just think of it as somebody with a dial inside here turning the voltage up and down. You set a voltage limit and a current limit. The voltage starts at 0, turn up the voltage, turn it up, 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 up. If you reach the current limit, stop. If you reach the volt limit, stop. That's it. You start at 0 volts, turn it up until either the current or the voltage limit is reached, whichever one comes first, and that's what the voltage will be set at. So it'll provide the full voltage and less current than your maximum, or it'll provide your maximum current but less voltage. And it's really that simple. More advanced power supplies obviously have more advanced features, but this is all you need to get started. Now, a multimeter is basically just a battery-powered device. It can measure, this one anyway, more advanced as usual is going to have more features. But this one can measure voltage, amperage, current, resistance, and it has a continuity diode test feature. We'll save that for last. Now, one thing to keep in mind about the multimeter is it has red and black probes. The black one is connected to what on this one is called common. It might also be labeled ground or negative or whatever your particular meter says. And the red one is connected to positive. So black is negative, red is positive. There's nothing special about the colors, it's just there to help you remember. If you have trouble seeing the colors, just put a sticker on there and write on it, just so that you can remember. Now, a multimeter dial has many settings. For example, voltage has 200 millivolts, 2 volts, 20 volts, 200 volts, 600 volts. And the reason it has these multiple settings is because of something called dynamic range. Your difference between your low and your high. If you're measuring high things, then if you're using components that allow you to correctly measure high numbers, then the low numbers are going to be incredibly inaccurate because they'll get lost in the noise. Whereas if you use smaller components, lighter components, that are capable of accurately measuring those smaller numbers, then you'll be incapable of measuring the larger numbers because it'll overload them. So you always want to use the setting that is as low as possible, but still higher. So for example, I have a 2 volt and 20 volt setting. So if I'm measuring something in that range, that's the setting I use. To measure 1.5 volts, I would use the 2 volt setting. To measure 25 volts, the 20 volt setting is not enough. I'd have to go up to the 200. The same for amps and the same for resistance. You always want to be only 1 notch higher than the thing you're trying to measure. If you use a higher notch, it'll still work, but it'll be less accurate. And your display might not have enough digits to correctly display it anyway. So the first mode of a multimeter is measuring voltage. Let's say we have our battery, and we have a resistor, and we have an LED connected just like so. So in this circuit, you can measure voltage anywhere you want. You could measure across the power supply and see that you're getting your full power. You could measure across the diode to check its forward voltage drop. You could measure across the resistor and you'll get the remainder between the two because the resistor is taking up all the slack. But you measure voltage in parallel. You don't stick it in your circuit. The multimeter includes its own resistor. So let's add the multimeter to this circuit. So the circuit itself is unchanged from power supply to resistor into diode, back to negative power. But over here, we also have our voltmeter, and we connect this in parallel. The positive to the positive terminal, the negative to the negative terminal. So you can see we have a parallel circuit here. The power is going through the circuit in this loop, And it's going through in this loop. One loop has the LED, the other loop has the voltmeter. Using your actual multimeter, you set it to a voltage setting, and these probes, these little tips, you just touch them right on the legs of the LED. You don't have to stick them in the circuit, you just touch them on. That's why they're called probes. Now you might think this is a short circuit, but obviously it's not, because inside the multimeter is a resistor. Just right on in here, it's got its own little resistor that it's using to control the current. And it's going to use a value of resistor that's high enough to handle the voltage you're putting in, because it is trying to be unobtrusive. The multimeter does not want to get in your circuit and screw everything up. It wants to be sneaky. So it has quite high resistance so that it disrupts the rest of the circuit by pulling power as little as possible. If you're measuring amps, though, it's a little different. Let's say you want to measure the current that is going through your LED in this situation. In this case, your amp meter is not going to have its own resistor. It doesn't want to change the voltage of the circuit because it is connected in series through the resistor into the amp meter, back out into the LED, and to negative power. You can see it's in series rather than in parallel. So in this mode, these probes are usually not going to be enough. If you have a broken circuit, you could touch the two ends. But for me, I use a breadboard, and these certainly don't fit in a breadboard unless you jam them in really hard and then rip your breadboard. So I have alligator clips with little header wires on them that I clip onto these probes. But this amp meter right now is using no internal resistance. It's just measuring the current. It wants to be as unobtrusive as possible. So it wants to basically be as near invisible as the wire in between. And this is something important. Do not just try to measure amps with your meter without a full circuit, because if you just had your power going into the amp meter and back out, well, if you're measuring a battery, that's going to be fine because the battery has its own internal resistance, as we've discussed. But what if it's not a battery? What if it's your bench power supply? Now you'd better hope you have a very good fuse in your multimeter, because if you do, now you don't, and it's time to go to the hardware store for a new fuse. And if you're less lucky, it's time to go to the hardware store for a new amp meter. The third mode of a multimeter measures resistance. Super important note, no current. Do not use this in a live circuit, because that will fry everything. You are measuring resistance. The multimeter is providing its own current across the resistor in a circuit like this. You'll notice that there is no plus and minus on the ohm meter here because resistors don't have a polarity, they go in either direction. So you just connect your meter to whatever you want to measure the resistance of. For example, a resistor. If you want to check to make sure that you're reading the color bands right, or make sure that the person you bought them from didn't cheat you. So the meter provides a voltage, it causes a current, the resistor resists it. Based on the value of the resistor in Ohm's law, it measures the amperage and figures out what the resistance is. That's literally all there is to it. If your multimeter does not have a continuity mode for checking if wires are connected, you can use this. Measure across wires, and if you get less than an ohm of resistance, then that means that you have a connection. If you have a wire with an ohm or more of resistance, you need some new wires. And if you get a super high resistance or more resistance than even the highest setting can measure, that means you have an open circuit because it's measuring the resistance of air. The final mode is a continuity mode. This is not on every multimeter, but I assume it's on every modern one. It's very simple. It works the same way as the resistance measurement. You set it on the continuity mode, and if there is a connection, let's hold it more steady. There's some oxidation on the tips of these because they're not gold plated and I haven't been very careful. So it's hard to make a perfect connection. Let me hold them really hard. The noise means there is a connection. It's just a circuit with a speaker, and when you connect it, the speaker is powered. This is great for making sure that your wires are still good, because the header wires I use are a little fragile. Sometimes they come unconnected inside, and you can check to make sure that they're still working. Or if you have some sort of jumper wire running across a board, you can check it to make sure it's connected. You can check the integrity of traces on a PCB. Traces are basically wires that are printed on a PCB. It's a conductive material. So you can touch two parts of traces or traces on either side of the board to see if there's actually a connection. You can also check for shorts to ground this way. For example, if you have, let's say you have a motherboard and you have used screws that are much larger, the head of them is larger than you're supposed to use. And let's say there happened to be a trace on the board pretty near the screw hole. Now a normal screw for the motherboard would be fine, but your bigger headed screw happens to be touching that trace. And you're not going to think of, oh, I used the wrong screw when your motherboard doesn't work. So what you can do is just touch one probe to the case. Doesn't even matter which one. Resistance is not polarized. Just touch one probe to the case and start touching everywhere else. Just and as soon as you hear a tone, you know you have a short to ground. It's a nice, quick diagnostic tool. It's a lot faster than watching the meter. In this case, if I was measuring resistance directly, I would have to set the setting correctly, and it updates only about once per second. But the continuity meter is instantaneous. On this meter, the continuity mode is also a diode test mode, which I think is silly and useless, because it can test only certain diodes, only the most simple ones with the lowest forward voltage drop. But it doesn't really waste anything because it's just connected to the continuity mode. They just set the continuity voltage to be high enough to trigger common types of diodes and call it a day. So I don't mind, I just ignore it. It's far better to test diodes with your bench power supply. So now let me show you a meter in action. Just to make my life easier, I have connected my multimeter probes directly into my breadboard so I can jumper to them instead of moving the probes around all the time. I also have my power supply, an LED, and a resistor to test. So first we will use the voltage mode to test. I'm going to connect the positive power to a resistor, the resistor to the LED, to the negative power. You'll notice this circuit does not involve my multimeter in any way. And I'm going to set this at 2 milliamps, which doesn't even matter because it's not even supplying 1, as you'll notice. So with the resistor there, we're getting the full 5 volts. Let's measure. So again, in parallel. So I'm going to connect the multimeter over the resistor. So I will connect the positive red probe to this side of the resistor, and the negative to the other side. And it's reading 1, which means I'm too low. I'm on the 200 millivolt setting. Turn it up, still too low. So now I'm on the 20 volt setting, and I'm reading 2.4 volts. So the resistor is dropping about 2.4 volts. If I move this over to the LED, see positive here, negative here, we get about 2.6. So that adds up to 5 right about. So you can see that. So without disturbing the circuit, we're measuring the voltage. But what if I want to measure the current? Always for safety, turn it down so your light goes off. So now we're going to measure the current, which will be less than 1 milliamp. So you connect from positive power directly into the multimeter. The negative lead of the multimeter over to the resistor to the LED, and the LED into the negative power. So we have one unified circuit, and there you go. So let's turn it up to 1 milliamp, and I still had my multimeter on the volt setting. So let's try the amp setting instead. And I'm going to set it to 2 milliamps because we have less than 1. But the next one down is 200 microamps, which is 0.2 milliamps. I might have more than that, so let's keep it high to start. So now we turn up the current, and you'll see it starts reading, and it is indeed over 200 microamps. It is 239 microamps, 0.239 milliamps, which is far less than the 1 milliamp limit I have set. Let's take the resistor out of the circuit. Remember, you're creating a short circuit, but it is safe because I have a current limiting power supply. So positive power to positive meter to positive LED, negative LED to negative power. And now up to 1 milliamp. The LED will come on, And you will see I am getting about 0.65, 0.66 milliamps, which is less than 1. This one's saying 1. The reason for that is this is a cheap Chinese power supply. Let's try 2 milliamps. 1.59. Let's try 3. So now I have to turn the setting up because that was a 2 limit. We seem to see a pattern here. And my LED is very bright, because 3 milliamps is a lot of milliamps for an LED. It can handle it just fine, but you really don't need it that bright. So obviously, with a better quality bench power supply, you're going to get a more accurate output. But honestly, this is good enough. So now we'll measure the resistance. This is a 10 kilo ohm resistor, my favorite kind. So I'll just set it on 20 kilo ohms, which is the next one up. Right now it's reading 1 with no other digits. That's how this meter signals that you have gone over its limit. There is more resistance than that. Let's set it all the way up, 20 mega ohms. And you can see that it's still saying there's too much resistance. That's because it's measuring the resistance, once again, of air and plastic. If I put my fingers on it, then it's going to read 5, 4, 3, 2 once it settles. Because now now that I'm closing my fingers on here, they're ever so slightly sweating, so they're becoming more conductive. Put it back here in the open circuit, and there you go. So let's measure the resistance of this trace in the breadboard. So it's reading 0, so we have to go down. Let's go down to the 200 ohm setting, and we see about 0.4 ohms. If we go over here to this trace, should be about the same, I would think. About 0.4. How about we add a wire? So we're going through the trace and a wire. Now we're getting 0.5. So you can see there's not much resistance in wires. But let's actually measure the resistance of this resistor. And of course, for a more accurate reading, you want to just touch the probes to the resistor leads. But this is good enough to show us, if I turn this up because it's reading 1, that we're getting 9.98 kilo ohms, because this is set on 20 kilo ohms. So your units on the dial, right now it says 20 kilo ohms. That means this number is kilo ohms. If it's set on mega ohms, the unit is mega ohms. If it's set on ohms, this unit is ohms. So on the 2 milliamp setting, whatever you see is in milliamps. So if you see 0.69, that's 0.69 milliamps. If you set it on 200 microamps and you see 0.12, you have 0.12 microamps. On the 20 volt setting, it's volts. On the 200 millivolt setting, it's millivolts. Just take whatever your number is and add the unit that you're looking at. It's very simple. Don't overcomplicate it. So we can see I got pretty good resistors. Those are supposed to have quite a good tolerance. I forget how much it is. They are supposed to have a 1% tolerance. So on a 10 kilo ohm resistor, 1% would be 0.1 kilo ohms. And it was off by, is it 0.98? Yes, so it was off by 0.02 kilo ohms. So I got good resistors, not counting the resistance of the wires and traces. And finally, of course, the continuity mode. So you touch the leads together. Obviously, that's continuous. In a trace that's connected, in a trace that's not connected, and there's really no more to it. You can also use it to test your wires. You can touch them to the leads directly. You'll notice that if I put it on my fingers, it's marked as not continuous, because even though there is current flowing through my body from this meter right now, it's so small it's basically not a wire. I don't make a good wire. So if I connect this in parallel, it's good. You can also put it through your breadboard, like so, to test your wire, and just do it like that. That's all there is to it. Now, one important note, you should not use the continuity mode to test your circuit itself. Because first of all, the more resistance, the more it might decide it's not continuous. The point is to check wires. All you're doing is making sure there's a connection between your components, or checking that there's not a short to ground. If you want to measure your circuit, you want to use the resistance mode with the power off. And then you can measure how much resistance is going through your entire circuit properly. And there you have it. And again, an oscilloscope is also a useful tool, but we'll discuss that in a future video when I actually have one, or I have made one. In the meantime, be seeing you.